algebraic geometry, or I don't know what. So he's done a PhD, and now he's a
Oh,
postdoc.
okay, because that's the the machine learning
Yeah,
AI
that's
capital of Canada.
Yeah,
that's
of the
not
world.
what that's not what he's doing. He's more doing well algebraic, and now he's leaning towards number theory, and that's so I don't
And
know where this is going to lead him, but that's his life.
well, it's
All right, we are live.
Okay.
So I apologize for interrupting, but it's time to start. So it's my pleasure. Hello, everyone. By the way, before we start, I want to briefly mention that this is going to be the last seminar of the spring semester. We're going to take a break for the summer. I know some people in Europe are still, they're not in vacation yet, and they are still teaching, taking classes. But I personally need a break, so I'm sorry, but I need to take a vacation. And I'll see you again in September. So it's been a pleasure, and I appreciate your support and you joining us every week. And without further ado, I want to welcome Frederic Mila from the EPFL, the École Polytechnique Fédérale de Lausanne in Switzerland. And today he's going to tell us about his recent work on Rydberg chains.
Okay.
Frederic, please.
Yeah. Thank you, Adrian. Thanks a lot for the invitation to give a talk in this series. It's, well, Zoom is a good thing to do as long as we cannot travel. So I am happy to give this talk here tonight. And I'm going to talk about a problem I learned about not so long ago. Maybe we started 3 years ago, something like this. It's an old problem that about a chiral transition at commensurate melting. It was a problem in the 80s about surfaces, and it reappeared recently in the context of quantum 1D Rydberg chains, where there is additional evidence in favor of this chiral transition, but it's still pretty much an unsolved problem. So I will do a little bit of history because I assume some of you might not have heard really about this problem, although in the early 80s it was one of the most, a problem that attracted all great theorists at that time. And then I will discuss it. This work has been done for the quantum part with a former student, Natalia Shepiga, who is now an assistant professor in Delft in the Netherlands, and with 2 graduate students, Samuel Nikes and Jeanne Colbois, who will finish soon. It's not working. What should I do to go to the next slide?
The slides are not.
Okay, no, it's
there.
just,
Okay. Cool.
I was just using the wrong button. So here is the scope. I will start with a review of this classical problem of the 80s with the commensurate and commensurate transition into the period 3 systems. And then I will describe the 1D quantum aspect of it with the Rydberg chains. And then I will describe you the numerical work we've been doing on these 2 problems. On the 2-dimensional classical problem, we have used a method called CTMRG. It's corner transform matrix renormalization group, which has been devised about 25 years ago, but not used so systematically. And this method turned out to be far more efficient than any classical Monte Carlo simulation. And I think we have something close to a numerical solution to the problem. And then I will move to Rydberg atoms, which we have given experiments very recently. And there it's based, the work I will present is based on DMRG investigations of constrained models, where we constrained particles, here bosons, to stay apart from each other. And this makes it possible to study very large systems. And again, we've collected, I think, good evidence in favor of such a transition. So what is the problem? The starting point was a paper by David Hughes and Michael Fisher in 1982. I think it was probably David Hughes' PhD, where they noticed that if we have a commensurate transition, the transition is not necessarily in a conformal in a conformal universality class. I think at that time maybe the word conformal was not used, but it was more. They suggested that although if we have three domains, the transition is not necessarily a three-state Potts transition. And the idea is the following: imagine that you have a solid that develops some kind of order, so that you have stripes in the ordered phase of particles followed by two empty stripes. You will have three domains depending on where the occupied stripe lies. And then if you have a transition, it has to be related to the development of domain walls. But now they realize that there are two types of domain walls that are very different, so that a sequence of domain, so here, for instance, two lines that are sitting close to each other are full, whereas here there is still an empty line. And so if you have domain ABC, a succession of transition ABC and back to A will be different from ACB back to A. So there is something like a Chiral perturbation in the system. I will not be formal today. I will be very descriptive from that point of view, but there is a Chiral perturbation, and generically, in that case, the transition cannot be a three-state Potts model if there is a Chiral perturbation. So the model, to make things more precise, and this is exactly the model we are going to study, what was then proposed as a model to describe this was called at that time maybe the asymmetric three-state Potts model. Now it's more called the Chiral three-state Potts model. In 2D, it's a model where at each site we have an integer that can take three values, say 0, 1, 2, and we have just a cosine with a 2 pi over 3, so that this model would naturally have, if delta was 0, a period 3 type of order. But then to describe the Chiral perturbation that you would have if you have domains, you introduce a parameter delta that can take non-integer values. And whenever delta is different from 0, there is a perturbation along X. And the transition, which is a three-state Potts transition for delta equals 0, can no longer be such a transition because this perturbation is relevant, as was shown by Hughes and Fisher. And so if it is relevant, it has to produce something. One possibility, which is written, the last one here, which always occurs, but maybe not immediately, is that the transition splits into two transitions. You have a transition, when you come from, say, the disordered phase, you undergo a Kosterlitz-Thouless transition into a critical phase. And then from this critical phase, which is still incommensurate, you have a transition into a commensurate phase. And this transition would be what is called a Pokorski-Talapov transition. But what Hughes and Fisher suggested is that maybe this does not occur immediately if one goes away from the Potts point. Another possibility would be that there is still a direct continuous transition, but then it's not a conformal transition. It has to be a different universality class, and they called it a Chiral transition. And it has several properties. I will review them on the way. But one of them is that it has anisotropic scaling. That is, the correlation length in the two directions, X and Y, should diverge with different critical exponents, meaning that we have an anisotropy exponent, or what is called today a dynamical exponent, because most often when we have two directions, one is going to be space and time. And so this exponent it's just the ratio of the exponents of the correlation length in two directions. This exponent Z is then larger than 1. Whereas in conformal theory, as you know, all these transitions to have conformal invariance, the system has to have a dynamical exponent, which is just 1. So this is what they suggested, just based on the possibility, how should I say, plausibility. So this is the phase diagram that they considered. Let's look just at the right-hand side of this phase diagram. So from our purpose, this would be a Potts transition, the P point. Then there would be from the commensurate phase to the incommensurate phase, which they call here disorder incommensurate. There would be the possibility of having a transition through a critical phase before the disordered phase. But they suggested that it could be a disorder point here, that would be called the Lifshitz point here. and that between the Potts point and the Lifshitz point, there is no intermediate phase. It's another transition, and it has to have other characteristics. So that's a prediction that there were attempts to check it. And one way to check it that we will use later is the following. Let's call delta Q the distance to the commensurate wave vector. Here for the period 3 case, the commensurate wave vector will be 2 pi over 3. So let's call delta Q in the disordered phase the distance to this commensurate value, and psi the correlation length. What they observed is that at the Potts point, the product of the two, well, delta Q goes to 0, psi diverges, so anything can happen a priori. But at the Potts point, the product of the two goes to 0. Now, if we have an intermediate phase, at the KT transition, psi diverges, but delta Q is still finite because the critical phase is still incommensurate. This means that this product diverges at the transition coming from the high temperature. And what they suggested is that in between, there can be an intermediate regime where the product delta Q times psi goes to a constant, a strictly positive constant. And that would be one of the characteristics and the practical characteristics actually of the Chiral transition. It looks fairly simple as a problem. What you have to do, take the model, put it on the lattice, calculate the wave vector, the correlation length, and check for this. It turns out that with usual Monte Carlo simulations, this is basically impossible, at least when people tried in the 80s, where classical Monte Carlo was already quite sophisticated. It's true that it hasn't been really tried again very recently, but I will show you some results even on the Potts point, where very clearly the new methods based on this tensor network representation really outperforms massively the Monte Carlo simulations. So at that time, one paper where they tried to do this was by Walter Delke and Julia Yeomans in 1982, very shortly after. And they came up with a tentative phase diagram, but the Q vector, they could really not properly measure. They have a very poor estimate of the Q vector. They had some evidence here of some divergence, but this phase diagram actually resembled very little the one we are actually observing now. But they were very, they could never see any evidence of a new universality class here of different exponents from Potts. So, I mean, they were very, very safe on their paper. I mean, the conclusion was basically that it's difficult, and I'm skipping a lot of papers done later on that came to the conclusion that it's difficult. And in fact, in the 80s, if you read the papers, the numerical papers on this subject, half of them conclude that there is a Chiral transition, half of them that there is no Chiral transition, but they basically have the same results. It's just impossible to conclude on the basis of what was available. Then to make things more complicated for the idea of a Chiral transition, there has been some work done on field theory on a Sine-Gordon model. 2 papers, one by Haldane, Bach and Bohr, Thomas Bohr, and the other one in parallel by Heinz Schulz. And for that particular model, both papers realized, they realized that there is always an intermediate phase away from the Potts point for that particular model. So that the idea of a Chiral transition is non-existent. According to them, as soon as there is a Chiral perturbation, the transition will split. Well, then Hughes and Fisher came back again the year after with this time a very exhaustive paper on this, and in which they came up with really interesting scaling arguments that the conclusion of that paper relies on the fact that there are really no dislocation whatsoever, no fluctuation and outside in the commensurate phase, but this cannot be true. If there is a fugacity dislocations constant to be created in the commensurate phase, that would be the axis here. And so what they say that starting from this point, what these papers by Haldane, Bach-Bohr, and Schulz found is that there is always an intermediate phase here with 2-phase transition. But this, as soon as we introduce the possibility of having dislocations already in the commensurate phase, it could be that the transition is first still continuous, but then along this line, it would have to be a chiral transition. It cannot be a conformal transition, and then in commensurate, something opens in between. So that's kind of the situation. What is interesting, this is, well, scientifically interesting for my talk, but also sociologically. Experimentally, I think this problem has been, quote unquote, solved years after theorists were interested, to the point where I think none of the theorists that have worked on this know about these papers. We found them by chance. There were two papers in 1994. In between, the field had gone into integrability because there are some integrable versions of these chiral Potts models. And so a number of conclusions were drawn on this. But experimentally, this kind of problem applies on reconstructed surfaces, for instance. It can be also adsorbate on surfaces, making this kind of period 3 order, but it can also be just a surface that has a reconstruction so that the last layer is reconstructed. And this occurs in particular along the 111 surface of silicon or germanium. In that paper, they have studied both systems, and looking at the silicon 111, they found that the product Q, which is delta Q for me times psi, seems to go to 0, whereas it's a constant here. So they concluded that the transition here could be chiral. But a paper published the same year by Bergeneau and collaborators, which has a very systematic investigation of correlation length and so on, came to a conclusion. It's very surprising because, as I will show, this is exactly what we found numerically. So they published in 1994 a paper where they actually measured the correlation length exponent along X and found something 0.65, close to 2/3. Along Y, something close to 1, so that the ratio of the two is 1.6, close to 3/2. And at the same time, they measured the exponent of the way delta Q goes to 0 at the transition, and they found an exponent which is, again, 0.66, very close to nu X, and beta being close to nu X means that delta Q times psi goes to a constant, because the divergence of psi is completely compensated by delta Q going to 0. So this paper has a beautiful experimental demonstration, I think, that a very strong case in favor of a chiral transition. And people nowadays, at least interested in that problem in the context of 1D quantum systems, were apparently completely unaware of this. I talk very often with Paul Fenley about this problem in the quantum, and he couldn't believe it when he realized that there was this paper lying around showing somehow that there is a chiral transition, because he was one of the guys really skeptical about this possibility. So that's it about the introduction for the classical model. Now, this is old story, kind of unsolved, or maybe solved, but people didn't realize. I don't know how to say it. But numerically, at least, nobody was able to come up with an explanation of these results. Now, completely different setting. This problem has really reappeared about, well, already a few years ago, because people were around Sajtev and Lukin were thinking about these models. But the first experiments the first experiment was published in 2017 by the group of Misha Lukin in Harvard. And what they managed to do with optical tweezers was to create one-dimensional arrays, so chains, of Rydberg atoms. By Rydberg atoms, we mean an atom which has a ground state, and they put it in the laser. So there is some subtlety there, but the bottom line is that with laser, they can induce a transition between the one state, the ground state of this atom, and one highly excited Rydberg state. And this is going to be translated into a term which is sigma x, or in terms of particle, it would create or annihilate the particle. But by having a small detuning between the frequency actually that they create, it's a two-step process, but I don't want to enter this. But if there is a small detuning delta, they can favor the ground state or the other excited state. So there is what they call delta I here, which plays the role of a chemical potential that will favor one of the states. And what is very interesting in these Rydberg atoms is that when they are excited, they have a long range interaction. The interaction between these atoms actually decays as 1/r⁶. So it decays fast, but still has a power law. So there is a long range interaction, and the range is long enough that they can stabilize phases having high commensurability. And this is what they have observed in that paper. They have observed that depending on the coupling strength here, they can create different types of ordered phase, a period 2 phase, or a period 3 phase, or a period 4 phase. And this is shown here in these experiments, but they can get out of this phase by playing with the detuning parameter, which is the chemical potential. So they can really produce this, and one see this on this picture where every other line is a colored one, while here it's every third line and here every fourth line. So they can create these phases, and then the transition here between the ordered phase, the quantum transition between this ordered phase and the disordered phase here is a commensurate incommensurate transition. So there is a very well-known correspondence between quantum 1D model and classical 2D models. So these transitions here are potentially commensurate incommensurate transition, and then either they could be some critical phase around them, but maybe they could be some chiral transition. So that was the main interest in this. And in a subsequent paper, still in Misha Lukin's group, and there are some theorists were involved in that, what I managed to do is to do some Kibble-Turek type of experiments by sweeping this detuning parameter. So, you know, the Kibble-Turek mechanism, let me maybe remind you what it is. The Kibble-Turek mechanism, the idea is that if you sweep a parameter across a continuous phase transition, if you do it very slowly, the correlation length is going to diverge at the transition. But if you do it at a certain rate, the system will not have time to equilibrate because there is a relaxation time to the system. And so by sweeping at a certain rate, if one sweeps very fast, the correlation length will grow, and at a certain point, it's going to level off. The system will not have time to equilibrate, and the value you reach for the correlation length scales at the sweeping rate with an exponent which is known as the Kibble-Turek exponent, which is a combination of nu and z. Exactly what you need to characterize a chiral transition. That is, nu is the correlation of the exponent of the correlation length along the chain, and z is the dynamical exponent here. It's a quantum system, and it's so they were able to measure an exponent that would be related to both nu and z. And they found some evidence on some plateaus about these exponents for the Z2 phase, the D3 phase, and the Z4 phase. And I will show you that this transition Z2, for instance, is not a chiral transition, it's an Ising transition. And the value here is consistent with the Ising prediction. For these phases, it's more tricky, but it's already remarkable that they were able to perform such a sweep, measure the correlation length by looking at the domain sizes. So there are experiments. I'm not sure, anyway, we're going to work on toy models at the moment, so I'm not sure how much one can claim that these experiments have been explained, and maybe they will have to be revisited to have more precise results. But anyway, they were able to measure this. And they believe that there is evidence for a chiral transition there. So that's the end of the introduction. Sorry, it was a bit long, but I think it's, I hope it's physics that probably not so well known across the community, but there are real problems. So let me start now. Let me show you what modern numerical techniques have been able to say about these problems. And I will start by the classical problem. The two are very much related. Really, they are basically the two faces of the same coin. Let me start by the classical problem and present very briefly a method that was, I think, invented by Nishino and Okunishi in 1996, which is called corner transform matrix renormalization group. The corner transform matrix was a concept invented by Baxter, And they tried to see whether using these ideas and using ideas borrowed from DMRG, this appeared really in the aftermath of the DMRG discovery by Steve White. They tried to combine the two of them. And this method actually, which was devised for statistical physics, is used a lot nowadays for 2D quantum problems in the context of IPEPs and all these tensor network methods, but that's another story. So what is the corner transfer matrix in 2 words? Well, in most cases, the partition function of a classical system can be written as a tensor network. That is, each site is connected to different sites, and then one puts Boltzmann weights at each side. It's like in 1D, the very standard solution of the Ising model. There is it's just a one-dimensional system, so it's just a matrix. But all these problems can naturally be formulated as a tensor, and well, if for instance, the Onsager solution of the 2-dimensional Ising model started from this, and then there is a transfer matrix, and the transfer matrix you could solve exactly, and then get the dominant eigenvalue. So that's one way, and Baxter had other ways to use the corner transfer matrix. But the idea of this method here is to group sites. We have these tensors here, and we try to group all these sites in one. Again, a new corner, which would have a much bigger dimension, because the dimension should in principle be the product of these 2 dimensions here and here, to group these 2 sites into, again, another tensor, to reach a new system with only one tensor here, and which here would be a matrix because it's a corner, it has only 2 legs, and then 2 tensors here. And then one repeats it. One gets this, and one again go from the new corner transfer matrix with one combine this with the neighborings to get a new transfer matrix, and one combine this to produce a new tensor. And this would be just exact, but totally intractable, because the bond dimension of the tensor would increase. And then this idea is very similar to DMRG, at least in his modern formulation. The whole idea here is to create a tensor with a fixed dimension by discarding the smallest weight in some kind of SVD, singular value decomposition. So it's an approximate way of contracting this tensor network. And this is what we have used. Much to my surprise, this approach in StatPhys has not been used very systematically on any model in 2D. Probably because most 2-dimensional models are considered to be solved. Actually, I think I came to this idea. We started, I give you the story in reverse order, because we started to work on the 1-dimensional quantum problem with Natalia Shepiga. And then I gave a talk at some point that was in Kobe, organized, a conference organized by Nishino, and Frank Verstrete was there and told me, but I mean, did you try to solve, like to look actually at the 2D classical problem? And that was a very interesting suggestion, because it turns out that it hadn't been done. And so we tried it. We tried to study the Potts model and the Chiral Potts model. Let me start with just the standard Potts model. This model has been studied, of course, and a number of the exponents are known exactly, actually, for that model. And here is a benchmark of the numerical simulations I've done. We have done, and one thing that is really different, that makes a big difference, is that the results that one obtains with this method, far from the not too close to the critical temperature, are extremely precise, because all we have to do if we calculate, for instance, the correlation length, is to make an extrapolation, say in chi. Well, there are slightly more sophisticated ways of doing it by looking at eigenvalues of the transfer matrix, but basically it's an extrapolation, and it turns out that this extrapolation is extremely smooth. It's almost horizontal, it's a line. So one can get results that are very precise, so precise that instead of getting the exponent by just fitting a window, one can use the concept of effective exponents taking the logarithmic derivative of a quantity with respect to the distance to the critical point to get an effective exponent away from the critical point, and one can follow this exponent. This has been done by some people in stat phys. I know some papers by Malte Henkel in the late 90s where they used this. And here this makes a big difference because all these problems are really have crossover regimes and corrections to scaling. But with this approach, one can really look at the tendencies without having to fit a window and wonder whether one has fitted too far, too close from the critical point. So it makes a big difference. So here are the results we got, for instance, for the Potts point. All these are effective exponents away from the critical point. Surprisingly enough, it's at that point for the correlation length is still a little bit noisy, but the exponent from low temperature and high temperature both go to values totally consistent with the exact result 5/5. Well, this is also what Monte Carlo would get. So this is not a big achievement. For the exponent beta, or I should say beta bar, this is the name under which it goes, which describes this means that we go for Chiral model where the transition is incommensurate, but we go to the Potts point. And then there is an exact result again for this exponent, which is 5/3. And these are our results, numerical results, and they are perfectly consistent. But again, as you see, it's really important to have the tendency with the distance to the critical point. And there, this is where we have our claim of fame with this method for the exponent of the specific heat alpha. In Monte Carlo, this is a big problem and a big puzzle. You know, there were papers by Alan Sokal and the students in the late 90s trying to really pin it down. And with Monte Carlo, for this exponent, you always get something that is bigger than 0.4 or around 0.4, whereas there is an exact result, which is 1/3. And here with this method, with this effective exponent, what we get is, first of all, an exponent that goes down, definitely below 0.4. And we don't know exactly how to extrapolate, but it's not inconsistent with this result. But even better, what we could do here is to study, rather than the specific heat, study directly the energy close to the critical point. And it should have an exponent 1 minus alpha. And there we get an exponent, so this exponent should be equal to 2/3. And here, we're going there, but look at the scale. We're already almost at 2/3, 0.65. So this means that we basically have the second digit of this exponent, although with Monte Carlo, it's very difficult. So I think that these methods, CTMRG, has a real power to give results when there are crossover that goes far beyond what can be done with Monte Carlo. That's just Potts point. So now let's go to the results away when we have the Chiral model. Then the results are still, you know, there are some hypotheses, some level of interpretation, because there are still extremely strong crossovers in the problem. But if we go to small values of delta, not too big values of delta, away from the Potts point, then we have consistent results. We have done different cuts, and the exponent beta bar changes rather dramatically there. It was 5/3, that is 1.6 at the Potts point, and almost immediately it goes to a value which is very close to 2/3, 0.66 or something like this. And this remains true for a while, and then crossover, some kind of crossover behavior takes away. So it comes in so that there is a big curvature, and then it becomes more difficult to determine the exponent. But for a while, it is essentially fixed at this value. And for larger values of delta, close to what we believe the Lifshitz point, there we have a very clear difference, anisotropy, and the difference between the exponent mu y in the y direction, which from high and low temperature come to the same value and around 1, and the exponent mu x, which describe the correlation length in the direction where we have the chiral perturbation, which decreases. Again, we have two different cuts to check the results, and it goes to a value around 0.7 or 67, not far from the value of beta. And if we go then for smaller value of delta, then the crossover for this exponent mu x becomes very big, and it's difficult to go to delta equals 0. So that explains why people looking at different results came to different conclusions. But our conclusions are based on these results. We think we have rather strong evidence that up to a certain point, we have transitions. And then if we go to larger values of delta, then very clearly, in coming from high temperature, the new y exponent diverges with not even with an exponent consistent with KT transition. So I want to cut it short here, but our conclusion for the phase diagram now of that model is the following. If we input delta here at the on the horizontal axis in the temperature, so we have here the Potts transition where everything is known exactly. And then for a longer line, we have exponents which seem to be consistent with each other. Something I didn't show is that there is hyperscaling. So the various exponents are related to the specific heat exponent that we could measure, and there is basically no change of the exponent along the transition. And then having beta bar, in this part, we could measure beta bar, which is 2/3. With the hyperscaling, this implies that nu x is 2/3. And here we have nu x, but again, with hyperscaling, it implies that beta bar is 2/3. So that along this transition, we come to the conclusion that the dynamical exponent is definitely not 1, that it is 3/2. And then this is true up to a Lifshitz point, which is around 0.16. And beyond that, we have the exponents that are consistent with the Pogorsky-Talapov transition. And here we have something that looks like a KT transition, but we are not really able on that model to determine the width of the floating phase. It's probably too narrow. So to some extent, this is the numerical, this is maybe the numerical solution of the problem. We have assumed that the exponents, do not change because they might change a little bit within I didn't put error bars, but the evidence, at least our results are fully consistent with exponents that would not change along the transition and would have these values. And these values, quite remarkably, are exactly those found by Cardy in 1993 in the solution of another related model, but instead of having a real delta here, the model that he could solve using CFT and some RG arguments is a model where when the delta here is replaced by a purely imaginary number I delta in the x direction and minus I delta in the y direction. So it's not a physical model. The Boltzmann weight are complex numbers, but for that particular model, he could show that the exponents have exactly these values. So it's in particular. So it seemed that it's maybe this is the solution. These values, and this we discovered after, after having done this calculation, are absolutely consistent with those for the surface physics there, for the reconstructed silicon that was determined by Bergeneau and collaborators. These are exactly the same values. And finally, what I should say also, there have been recently, in the motivated by the results on the Rydberg atoms, some very interesting field theory results by Sachtev and collaborators, where they do some kind of epsilon expansion coming from dimension 3, and came to the conclusion that there is anyway a dynamical exponent larger than 1. Their values are, in its one loop, they are not meant to be exact, but the values are not, they would be in reasonable agreement with our prediction here. So that closed the first part of the talk that I wanted this closes what I wanted to say about the classical 2D system. We are now investigating a system of period 4, Ashkin-Teller. And again, I think Hughes and Fisher got it entirely right there. It's quite amazing, this paper, just about scaling arguments, how far they could go, and apparently really understand the physics of these models. Okay. So let me change gears now and go to the quantum problem. So back to the quantum world that is maybe more appropriate to this seminar. I hadn't realized that till today, or I mean, I didn't pay attention to the title of the seminar, which is about quantum. So, but quantum 1D physics and classical 2D physics is the same thing, no? So I think it should be okay. So now we go to the Rydberg chain. And so I remind the model. The model has a term which just creates the sum of two terms that creates an annihilates particle. So this model doesn't have U1 symmetry, at least not an apparent one. It has it creates and it doesn't conserve the number of particles. There is a chemical potential and the long-range repulsion. And what we are going to do in the talk here, and I will come back to this problem in the perspectives, but for today we are going to study toy models that kind of contain exactly the most important physics that has to do with the following. Imagine that you have a period P phase in the system. To work with long-range interactions is difficult, and you will be limited to rather short chains anyway, because although it's the MRG, if you have a model with 2 degrees of freedom, there is a limit to what you can do. But this can be replaced, and this was suggested, I will come to it by in a second, for a certain case by Sengupta, Fendley, and Sachdev years ago. We're going to work in a model which is a caricature of this interaction. For any distance smaller than P minus 1, we are going to consider that the repulsion is infinite. Because anyway, the probability of 2 particles to be at that distance is so small that it plays no role, but it reduces the Hilbert space considerably. Then at the distance, which is important for stabilizing the period P phase, that is at distance P minus 1, we are going to take this non-zero. This will be the interaction parameter of our model. And for all other terms, they will be set to 0 because they are not expected to play a major role. So quantitatively, clearly, this is not going to be okay, but qualitatively, it contains all the physics of that model. The only thing is that to describe a different period in the Rydberg atoms, you remember we had period 2, 3, 4. One has to take a different model. That is, for period 3, this is the model that was suggested in 2004 already by Fendley, Sengupta, and Sachdev. For period 3, we're just going to work with what they coined hard bosons, which is a model of hardcore bosons, because this system actually these atoms behave as boson. There is no fermionic statistics, but they can be in only 2 states. So this is anyway hardcore boson, or one could reformulate it in spin language, of course, like spin 1/2. But we're also going, and they also suggested to have because of the blockade somehow, to assume that there are no nearest neighbors, so to prevent the system from forming nearest neighbors, and then to have only a repulsion between next nearest neighbor. This is exactly a distance 2. This is exactly what I explained in general. So this is one model we are going to look at. This is actually a very fascinating model. We came to all this field with Natalia Shepiga from a completely different route. And this model has appeared in the literature under disguised in many contexts. And this is something we summarized with Natalia in this paper. And we were actually, what we started from is to work on a quantum dimer model on a ladder. And studying a quantum dimer model on a ladder, if one excludes from the Hilbert space the non-flipping configurations, one ends up with a model which we found out at a workshop with Paul Fendley is exactly equivalent to their model of the 1D chain. It can be reformulated. If you're interested with this, it's amazing. So this quantum dimer model, exactly equivalent to that one. One can reformulate it as a quantum loop model to study spin 1 model that we were interested in context of spin 1 chains. It's again exactly the same model. So we have all these phase diagrams for the same price. And in this phase diagram that I will show you, there is a model that our chairman knows very well, which is the Fibonacci anion chain. Well, I didn't put the reference here, but anyway, I say it by, I know it's, I'm not going to dwell on this anyway, but this model describes, depending on the sign of the density matrix elements, is sitting at the tricritical Ising point or at the Potts point, which are 2 special points of the phase diagram we've worked out. And it's exactly the same model again, rigorously. It's not approximately, but it's exactly the same model. So it's quite funny that all these 1D models are all related. So what we did there is explain exactly all these mappings and look at the various phase diagrams, reformulate it, but that's it. But okay, let me keep with the hard boson model and the suggested by Fenley, Sengupta, and Sachdev. And here is the phase diagram that was actually already worked out quite in detail by Fenley et al. In 2004. And this is taken from our paper with Natalia. So this phase diagram here describes essentially the period 3 phase, but it is also able to describe a period, part of the period 2 phase, this hard boson model. And it consists of essentially 3 phases, 2 ordered phases, as I say, period 3, period 2. And then a disordered phase here, which is incommensurate in this dark blue part and which becomes commensurate here. And this is the disorder line where inside this phase that has no long range order, the correlations become incommensurate. So since this phase here is entirely commensurate, the transition into the period 2 phase is generically Ising transition, but an Ising transition can always terminate at the tricritical Ising point to become first order. And this is exactly what happens in this model. And the Fibonacci chain anion chain I was talking about is sitting at this tricritical Ising point here in this phase diagram. The dotted lines here are integrable lines, by the way. They are not transition lines, but they are lines where there is a beta ansatz solution to the problem. And then the period 3 phase is entirely surrounded by an incommensurate phase. So this is really an example of incommensurate transition, except at the line where inside the disordered phase, the period is 3, the wave vector is 2 pi over 3, because it turns out that the wave vector goes from being smaller to larger than 2 pi over 3, and there is a line where it is the system is commensurate, and along this line, the transition is known to be 3 state pots. So, and that's a Potts transition. So that's basically what was known. And then what was also shown by Fenley and Sengupta and Sachdev is that far enough here, there has to be an intermediate phase between the period 3 phase and the disordered phase. It's very narrow. And, but the conclusion was that in the absence of any reason to believe that something else happens, they conclude in that paper that this incommensurate phase probably goes to the 3 state pots. I think Paul Fenley was one guy that was really skeptical about the possibility of a chiral transition in that model. And that's where we entered with Natalia. I can skip this slide because it's just repeat what I said. So in this 2004 paper, the message was that there is probably an intermediate phase up to the Potts point, nothing like chiral phase transition, but then motivated by these new experiments on Rydberg atoms, and that were around and that seemed to find that there is a continuous transition, in fact, along a certain portion of the period 3 phase. Sachdev and collaborators with the PhD student Samajdar, they revisited the model and doing something very different from what we did, still DMRG, but some scaling on smaller systems. They got some evidence of a non-integer dynamical exponent between the Potts point and V goes to infinity. So that is, along this line, they had some evidence that there should be maybe a dynamical exponent that is not fixed to 1, but that the transition is not Pokovsky-Talapov, because Pokovsky-Talapov would immediately have Z equal to. And so now what did we do with Natalia Shepiga? Well, the difference is that she wrote an algorithm that really explicitly takes the constraint into account. That is, she builds the MPS satisfying the constraint at each stage. So this takes advantage of the huge reduction of the Hilbert space. The Hilbert space grows as Fibonacci, this Fibonacci number to the power of the number of sites. So it's really much smaller than the usual system. And she managed to do simulations up to 9,000 sites for some parameter. So really very big and converged. I mean, she stopped, when I say simulation, that is, these are sizes where the DMRG simulation was really converged by any standard, usual standard. And on the basis of this, she was able to extract the Q vector very precisely, at least to the third digit, if not better, and to get access to correlation length that are of several hundreds, really very big, or even thousands in some favorable cases, and still being conservative, that is, staying away from the boundaries and so on. And so on the basis of these simulations, it became possible to have a meaningful evaluation of the product delta Q times Xi close to the phase transition. So this is what is summarized now on this slide. At the center is the POTS point. So the POTS point, we look at, well, there is no temperature here, but there is a critical point. So there are two sides of the transition, an incommensurate side and a commensurate side here. And so what we, first of all, the correlation length here at the POTS point is exactly what we expect. That is, it's a benchmark for our algorithm. The critical exponent is 0.8333, and when we get on both sides exponents that are consistent with this value, the beta bar that should be 1.66, etc., is also consistent. So the delta Q goes to 0 with the a curvature, that is, it reaches 0 very smoothly with an exponent which is clearly larger than 1. And if we look then at this plot, which is the product delta Q times Xi, at the transition, it clearly goes to 0 within error bars. So all this is very consistent with what is known of about the POTS point. Now, if we go far from the POTS point, on the left-hand side, which was a part that was looked at by Fenley and Sengupta and Sachdev with some beta on that solution, it's completely different. So the inverse correlation length here, on one side goes to 0 with an exponent which is consistent with 1/2, which is what one expects for the Pokorski-Talapov transition. But coming from the incommensurate side, the 1 over Xi goes to 0 very, very fast, which means that Xi grows very, very rapidly. And the curve is actually convex, it's no longer concave. So it's a completely change of behavior. And this is typical of a KT transition. If we try to fit, this is where we would locate the KT transition. So there are, in fact, two transitions. The correlation length then is infinite in the window. The exponent beta bar coming from the incommensurate phase goes to 0, not at the KT transition, but at the Pokorski-Talapov transition with an exponent which is roughly consistent with 1/2, the expectation for the Pokorski-Talapov transition. And the product delta Q times Xi diverges very fast upon approaching not even the PT transition, the KT transition, which is shown here. So very clearly, Xi diverges while Q is still incommensurate. So at least these two scenarios are very well documented, and they were the two extreme cases in Hughes and Fisher paper. Now, let's look at what happens just above the POTS point. This is along a cut that is above at a significant distance, but still not too far. So first of all, looking at the correlation length, the inverse correlation length seems to go to 0 at the single point. And in both cases, with an exponent, so it's a little bit difficult. It looks straight, but it's not like here. The exponents are still consistent with each other. It's a little bit noisy. But what is quite interesting is that in that case, the exponent beta bar that describes the way delta Q goes to 0 is smaller than 1. That is, the curve has changed concavity. Now this exponent being smaller than 1, it's not at all obvious what will happen with the two. The determination, the two values of beta bar here depend on how far you fit. Here we are not at all in the conditions where we could define effective exponent. That was true for the classical system. So depending on the fit range, we have the problem that the exponent beta take different values. But if we measure, just follow Hughes and Fisher and measure delta Q times Xi here at the transition, there is no evidence that it diverges and no evidence that it goes to 0. So it really seems that there is something here like a transition which is continuous, but it has to be in a different universality class because the the product delta Q times Xi doesn't go to 0 and the exponents are different. So that's just summarized. I think I'm out of time more or less. So a few more minutes, Adrian. It won't be long. So this just summarizes this. So our summary of the phase transition for hard boson phase diagram is the following. I just put back the old phase diagram. And for these points here, we have also some estimate of the widths. We think that away from the Potts point, but here, there is something which is a non-conformal phase transition called Chiral transition with a dynamical exponent, which is probably somewhere between 1 and 2 before the transition splits with an intermediate phase. Do you give me 5 minutes? So yes, we've done a similar analysis. It's a little bit more tricky for the period 4 phase. And again, because there is no exact solution. So there we had, first of all, to locate the commensurate line in the phase diagram, and this is shown here. That is, if we have, the parameterization is different. This one is closer to the experiment. That's why the phase appears on the other side, sorry. And there, so out of the period 4 phase, we measured the Q vector, and there is again a line, which is a commensurate line, where the Q vector is pi over 2, like in the period 4 phase, and it is smaller above it and larger below it, and then it reached the period 3 phase. And along this line, the transition has to be conformal. There is no, it's a commensurate transition. It's a standard order disorder transition. So, but then it's not, the fact that we have period 4 means that it's probably Ashkin-Teller, but Ashkin-Teller is a family of models. So it's in Ashkin-Teller universality class, but it's not clear in which universality class is. So the next task was to try to determine which Ashkin-Teller transition this is in. And along this line, I think the slides are in slightly the wrong order, but along these lines here, at the Ashkin-Teller point, we have the same kind of plot, and 1 over Xi gives an exponent nu, which is about 0.79, 78, 79. And this means that if we look at the Ashkin-Teller universality class, where the Ashkin-Teller model is a classical model defined by this energy, where we have 2 Ising degrees of freedom that have Ising couplings, plus a foresight term that is we couple simultaneously sigma and tau, and this parameter is called lambda. And this is a crucial parameter because from lambda equals 0 to 1, one has varying critical exponents. This is a whole family of critical models. So the first task for us was to determine where we are in this Ashkin-Teller model along the commensurate line. And the reason, since we have an exponent nu, which is, well, it's written 0.78, small 79, but anyway, this means that we are at a value of lambda, which is kind of intermediate. So we are along this line in the universality class of the Ashkin-Teller model with a lambda about 0.6. Why is it important? Well, it's important because for that model, the chiral perturbation is not always relevant. I think this was worked out by Heinz Schultz. He calculated the crossover exponent of the chiral perturbation. It has this value, and this exponent is only strictly positive, which means that the perturbation would be relevant. If nu is larger than the value of nu c, there is an exact result for that, which is slightly larger than the value at lambda equals 1. So if the model was ending up being, for instance, at this point, which is called the 4-state Potts point, then the chiral perturbation would not even be relevant. But we are far from it, and with such an exponent nu, very clearly the chiral perturbation is relevant. So we're back to a situation where we expect that away from the Ashkin-Teller point, either there is a floating phase or there is a chiral transition. And here is, I show you very similar plots, and I will go very fast because it's it's very similar to the period 3 case. If we're very close to Ashkin-Teller, the beta bar exponent, which is larger than 1 at the Ashkin-Teller point, becomes smaller than 1. We have here an exponent around 0.6, but the product delta Q times psi does not seem to diverge. It's consistent with the value that it goes to a finite value. Whereas if you go far away from it, we're back to a scenario where the inverse correlation length is convex now, typical of a KT transition and Pokorski-Talapov here, and the product Q times delta Q times Xi diverges very rapidly here. So this is why in this phase diagram again, we believe now that in this model with period 4, we again have a conformal point, Ashkin-Teller, that depending on the details of the model will have a different value of lambda. But for that particular model, at least, there is a chiral transition above and below the Ashkin-Teller model before we have a floating phase. This leads me to my conclusions. So using modern numerical approaches, I think now we have strong numerical evidence of a chiral transition, much stronger than before. In fact, it was not possible in the 80s. And for these 1D models, they are very recent. So anyway, they use modern techniques. So in particular, CTMRG is, much to my surprise, a very efficient method to study this kind of problem. And we have good evidence of a chiral transition for the 3-state POTS model. For 1D quantum problem, for the blockade models of Rydberg chains, constrained DMRG is a very powerful technique because we can study very big systems. And we came up again with, I think, strong evidence in favor of a chiral transition for period 3 and period 4 phases. What remains to be done? Well, we would like to go back to the actual system. Now that we understand how it works, thanks to these constrained models, we can study models with the realistic model, and we are currently doing this with one of the R6 interactions. A phase diagram was already proposed by Rader and Leuchli, still unpublished, archive 2019, where, as expected by field theory, around the period 5 phase, there is always a floating phase, and they could show that there is part of the period 4 phase is surrounded by some floating phase, but they had nothing to do here. This paper was based on calculating the central charge between these insulating phases. So they could say something about the floating phase, but they have nothing to do, and they could not follow the floating phase beyond some point. So the next thing for us to do is to study the tip of these lobes, which are then exactly those of the system studied by Lukin and collaborators, and try to find out what the transitions are here, come up with, if possible, actual calculations of nu and z, and then make proposal for the Keeble-Zurek exponent and check with them what they have measured. Finally, what are the open questions apart from this? This transition, as I said, numerically, I think we are getting close to a solution to the problem, but there is still no very deep theoretical understanding of this transition. There is no field theory for the chiral transition itself. There is no general result as to what the dynamical exponent could be, the nature of the Lifshitz point itself, whether it's what would be the dynamical exponent there, and also whether the chiral transition defines a single universality class with the same exponents, or whether there is a small variation of the exponents along these lines. So there are still many open questions in that field, but maybe now with the motivation and of the experiments, and they are now able to grow larger and larger chains and the numerical simulations, maybe it's worth looking at this problem again, also with the more theoretical, analytical arguments. I'm done. Thank you for your attention.
All right, thank you so much, Frederic, for a very nice talk and beautiful results. Now the session is open for questions. Before we start answering questions, I'm going to read a couple of comments from Theodore Einstein in the chat. He mentions that similar classical Monte Carlo results were done by Perarn, Rickvold, and coworkers. So maybe that's a reference that
yes,
look at.
So there are many papers. You know, I just yes, that's correct. I didn't mean to be exhaustive on the references. I think I cited just Delke and Yeomans. There were later papers and about this, and many models actually were studied. I think yes, that's correct. So though if you're really interested in this, then, well, one possibility would be to look at our recent paper, the nuclear physics paper on this, because there we've been very exhaustive in trying to cite most of the results that were obtained at that time. That's
Will do. Yeah, the second one is also my question. So there were extensive experiments at Maryland, which were ahead of the experiments that you mentioned. There was in 1990 already definitive results that the chiral three-state Potts transition was unusual, had the fact that the Q times C approaches a constant rather than 0 and infinity, well before the other groups did it. And we got did all sorts of other models. We did an Ashkin-Teller model, we did a four-state Potts model, we did an Ising model, and all our results were consistent with the current theory. We didn't get, your talk was wonderful, and it's really impressive how far you've gone. And I was sort of awestruck watching it, but it was pleasant to be part of the early phase of this subject.
So it could be that we missed. I mean, I believe you that we missed some papers or some earlier references. It was a very much studied subject from 80 to early 90s, and then nothing. And we tried to find our way through the literature. So you're saying that some experimental results already had good evidence of a chiral transition.
Yes.
Okay, very interesting. So
I'll send you the paper.
Oh, I would love it, because it's absolutely not done on purpose that I wanted to ignore.
No, I understand that, and there's a lot of literature, and I think we got short shrifted by the later community.
We came across these papers a little bit by chance. Walter Zelke mentioned to me after we posted a paper, this work of his. He did not even mention the other paper by where all the critical exponents that I mentioned, this paper by Bergenot and collaborators. But you're saying that there were even earlier papers on similar system that was again on this surface.
We all did 2D systems using mostly low energy diffraction.
Okay.
Sometimes specific heat anomalies, and we did transfer matrix, but not corner transfer matrix, of course. But
so please send me the papers.
I'll be delighted to.
Yeah, that would be very, very nice. Thanks for your comment.
All right. There's one comment in the chat by Subir. Subir Sashdev had to leave early and he apologizes. And he says that he remains skeptical about the self-dual theory of Cardy being the same as the chiral theory, as you discussed by email, according to him. And he has some arguments.
We changed a little bit. I didn't have a chance to talk to him recently about that. I don't think it's the same theory. It's we tried to understand the connection, and we were not able to find a direct connection between these. So at the level of what I said about this model, it's an observation that the exponents we get are very. Let me show what I'm talking about for the rest. Yes. So we're not saying, in the caption, this is just to summarize the results, but it's clear that we do not have this precision. We cannot claim that the exponents are equal to this, but they're all consistent with these values. And these values are exactly those found by Cardy, but in a really different model, it's indeed the case. And I think the field theory arguments by Subir and collaborators really are very different, and they point to exponents that have no reason to have these very special values. So to me, this is still an open problem, and Subir's comment is well taken, of course.
All right, we have a question by Noah Breali. Please, Noah, unmute yourself and go ahead.
Hi, Adrian. Hi, Professor Mila. So the question has to do with Cardy, of course. So Cardy showed sometime in the early 90s a result that Joe Moore and Frank Pullman turned into kind of a bound on DMRG near conformal critical points. As you may recall, it was this fancy DMRG that they were using, but the upshot was this chi has to grow when you study the Potts point or KT transition. So what I was surprised is, first of all, that you're able to get such precise critical regime results. And the second was I wonder if you can talk about the entanglement spectrum, how these eigenvalues look, and if maybe the chiral transition helps you evade some of those
So yeah, thanks. So your question refers to the quantum model, no? I think more DMRG. Because I suppose the work by Polman refers to DMRG. So
I guess for the classical too.
For the classical,
the idea is that these things are so.
Yeah, they're very much related. So you know, I think what I say. So maybe I could show this again. You know, we do not try to go very close to the critical point because the simulations stop being reliable. In fact, there are even convergence problems. So here, you know, very typically for the POTS point, we can get close to TC, and all the points that I show here, when you look, or for instance, for the exponent of the correlation length, where we can also get quite close, we only take points where the scaling with the bond dimension chi is perfectly linear and almost completely flat. So that, of course, there is still, you know, we cannot, chi is finite. We go typically up to, for these simulations, classical, up to chi equals 250. But really, there is very little chi dependence. And if we go closer to the critical point, then we still to have some curvature in chi, or in fact, we do not look at chi, as I said, 1 over chi, but we do rather scaling between gaps of the transfer matrix. If you take larger eigenvalues of the transfer matrix, this defines a gap. So there are some techniques to do that. And what is the bottom line is that the results we still quite far from TC, but they are so precise that we can define an effective exponent. This is really crucial for this type of analysis here, for instance. So we're not claiming that we are able to go very close to the critical point, but up to a certain value, the results are very precise. And this is on the basis of this that we think we build some fairly precise knowledge of what happens at the critical point. But you never go, you know, and we don't get this exponent, that's difficult. And for...
Yeah, I was wondering, is it different for the chiral point then? Can you get closer, or are you pushed further away?
It's very similar, actually. It doesn't make a big difference. The thing is, so the problem is more the crossover regimes that we have, that against which we have to fight. Because if we look, you know, at this phase transition, and this is something I said, but maybe I was not very precise. But if you look, for instance, at here where we think there is a single transition, there is real evidence. But the exponents nu y and nu x only slowly get apart from each other. So, but we know that if we have a continuous phase transition, hyperscaling has to relate all the exponents. We can calculate alpha. And there, in that regime, we have a very precise value of beta bar. And if it's a chiral transition, this has to be connected to nu x. That's or, you know, because we have a single transition. And with this, we come to the conclusion that here the correlation lengths probably have a very strong crossover scaling. And indeed, the two values of nu x and nu y only get apart from each other. So from that point of view, it's difficult, the chiral transition. It makes things more difficult because we have crossover regimes, and close to the POTS points, the critical exponents of the correlation lengths seem to be very much influenced by that point. But putting all together, if we assume hyperscaling, if we assume that there is a single transition and that then it has to be a chiral transition according to Hughes and Fisher, then we get a consistent picture, but it relies on the assumption that we have some strong crossovers so that some exponents would be wrong. And I think this explains why, partly why in the late 80s, where some works were already done on the transfer matrix, people had a hard time concluding, because if you look at it face value, it does not make any sense. So our approach based on this very reliable value, I think the most remarkable thing here that we got is the value of beta bar, which is 2/3, because I don't think this was obtained by any people earlier on that model. That was a strong argument plus the specific heat. But chiral transition doesn't make it, otherwise from the point of view of the convergence with chi, I think there is very little difference from the POTS point to the chiral, up to the Lifshitz point. And okay, I should stop there maybe.
All right. Any other questions from the audience?
Well, I guess the obvious one is how would Guthrie-Vidal's ansatz affect this scaling if you used a multi-scale entanglement or normalization ansatz? Something along those lines.
Ooh, this I really don't know. I have no experience with that, so that's a good question, but for for real experts. So that I'm sorry, I'm not able to answer that one.
I mean, I think that so you're trying to apply MERA to this problem when the constraint DMRG works very well for 9,000 states. Is that what you're trying to
we're thinking about
propose?
just like the Potts point, right? So the Potts point is conformal. So then this mirror seems to be designed to deal with this conformal, the logarithmic violation of the area law that you get in one dimension.
Right.
It's kind of designed for that. So at least at one point in this phase diagram, let's say the three-state Potts point, the mirror would win. So you could actually fill in the critical point. But then the question is, we have very little theoretical understanding of this chiral transition. Could we somehow generalize it so you could go away from that special point? And at least numerically, it sounds like there's not too much difference in the gap scaling and the entanglement spectrum. So there's a hope that you could generalize it. So you wouldn't just be stuck at the three-state Potts point where we already know the critical exponents to dead and be able to walk away towards this chiral transition line. But I guess Guthrie hasn't thought about it. Probably no one has.
Well, that's an interesting project. Nice proposition.
A decent proposition. I have a question about Andreas Loikley's paper. I haven't read it, so I'm just asking. So you said that they're looking at the phase diagram by looking at the central charge, but if you have a transition like the one you're describing here, where the central, it's not conformal. This approach will miss it completely, right?
I was very fast there because I thought I was beyond the time. They calculated C=1 inside the floating phase. That is, this phase is a Luttinger liquid, if you will, in the modern language. It's a Luttinger liquid with C=1. The exponents are not well known, and that's something we are trying to actually work on. But they were calculating the central charge of this phase here that would be characterized by C=1. Then, as you say, if there is, again, an Ashkin-Taylor point here, this is the model with 1/R6 interaction. So it's a different model. This is not the one we have studied yet. But if there is an Ashkin-Taylor point, it will be conformal. And then we would have the central charge. But away from it, if it's chiral, it's non-conformal. So the central charge is not defined. You're absolutely right. So they use the central charge for these floating phase, which are Luttinger liquid phases. That's what they did. So they were, and it's even complicated. I mean, this phase diagram, I'm giving now a talk on their paper, but with these very long range interactions, you can have even higher commensurability and Deville staircases in the limit of very large delta. So presumably the floating phase stops somewhere and gives, gives rise to some additional very high periodicity phases. So this phase diagram is really complicated. But what they did here is maybe an underestimate. They're not exactly sure, but at least they showed that there is a floating phase. And the fact that they found one here all around the period 5, this is already a very good point in favor of their paper, because this is really one of the predictions of the theory, that what Hughes and Fisher predicted was really limited to 1/3 and 1/4, but not at all to 1/5. It's different, and there has to be there are other arguments to say that there has to be a critical phase there. So that's what they did.
All right, I have a final question, and I apologize for this demonstration of ignorance, but when you have a quantum phase transition, a quantum critical point, I mean, there's no reason to expect that the critical exponent, the dynamic critical exponent, should be 1, right? And so if you have a dynamic critical exponent that is different than 1, what makes this chiral transition special?
So, well, I think we know, if I go, I don't know all models, of course, but in most cases, when a transition is continuous, in these cases, well, in these one D systems, it's in most of the case it is a conformal transition, like in 2D. This is the hypothesis, and otherwise the other case, which is well documented, is Z equal to, where this is the Pokrowski-Tarlapov transition, which in the quantum language it's just a transition where a fermionic band starts to get to fill up. So you go from 0 and you have the square root of the density of state, and this is the in the quantum language it's very simple, this Pokrowski. But all the transitions, I'm not sure that it is well documented. So there is nothing against it in principle if you have anisotropy, but it's very hard to find physical models where this can be demonstrated or exact solution. So it is going to be very different, and just it's I suppose it's curiosity-driven research.
I'm thinking in terms of
position that it's this to characterize it, and on top of that, I think it's still debated. I don't know if it is controversial, but it is still debated. Nothing excludes so far completely that the floating phase goes all around here, maybe up to a certain point, which is conformal, and the same here. So numerically, I think the evidence is really in favor of a chiral transition, but it is numerics. Mm-hmm. So in particular, if there is a very narrow floating phase, we will never see it. So it's numerically demonstrated up to a certain precision. We never claimed anything else than this anyway. That's would be too difficult. So it's just for the sake of finding a continuous phase transition in this in this new universality class. I don't think, well, Cardy's calculation for the model with the complex Boltzmann weights is one of the cases where this could be demonstrated, but this model is really not physical. So, and as Subia said, it's not obvious whether it's related to.
Right. No, my question is in the context of, if you have, for instance, a Heisenberg model with long-range interactions, then you don't have conformal invariance, but your system is still critical, and your dynamic critical exponent is different than 1. So the question is, yes. Right? What would distinguish a chiral critical theory from a theory, on this model, for instance?
Well, I'm not exactly sure. The field, if you think in terms of field theory, then it's there is a family. This is actually worked on by people more in high energy physics. They are called Lifshitz theories, where with dynamical exponent that could be in principle anything, or at least fractional, or but very little is known about these theories. So there is a free theory. For instance, if Z equal 2, there is a free Lifshitz theory, which is very much like an extension of the Luttinger liquid theory that has Z equal 1. So you take another term in the action, and therefore that, if you assume it's still a free field without interactions, you can calculate the critical exponents and all operators. So this is one theory. There could be generalization of the theory to Z between 1 and 2, but I think nothing known. There is not even a classification of the theory, so very little is known. So the fact that Z would be somewhere between 1 and 2, I don't think that it fixes completely the theory, but it's very interesting to study because precisely very little is known about the theories. Whereas when Z equal 1,
all right. So chiral applies to Z between 1 and 2. Is that right? Any value of Z between 1 and 2, or on top of Z, there's something else defining a chiral theory?
No, Chiral refers to the physical implementation that there is a chiral perturbation. But so
All right. Mhm.
they suggested, so let's call it a chiral universality class. But I don't think nobody knows the exponent. I think Hughes and Fisher had never claimed to know
Right.
what the exponents are. So they call this. It has to be another universality class, but. That would describe some model with some kind of chiral perturbation. But if you have another theory with Z between 1 and 2, I believe it could be very different. It could have a whole different sets of correlations and exponents, and it could be very different.
No, now that I think about it, these models with long-range interactions, the Heisenberg model, Z is more than 1, I believe. So
More than 1. Okay.
yeah. So the excitations go, the spectrum goes as you know,
So omega
as a
is
square root, something like that.
yes, exactly. This model, this reminds me. Yes, so exactly. So that would be a dynamical exponent smaller than 1. Whereas here we would have something that is convex. Yes.
Right. It's more like a ferromagnet or something in between. All right, very interesting. I'm just trying to learn.
So am I.
Because this is the first time I hear this story, so I find it really, really appealing, and it made me curious. All right, so if we don't have any other questions from the audience, let's thank Frederic one more time, and
thank you very much for the offer, and I really hope I will get more references from Theodore, so to learn more about this period, because I never talked about any expert of that period, so that's I will read. I will really look at anything you send me with great interest.
Okay. Thank you.
You're very welcome. Thank you, guys, and
all right, we meet again in September. To those that are following us, and I hope you miss us. But maybe we come to in-person seminars, not too far in the future. That'd be fantastic. But I think this has been a great venue to meet for the time being. And with this, I want to thank you all, and bye-bye.
Okay, thanks a lot. Thanks to everybody for coming tonight, or today for you, and thanks, Adrian. And
thank you for staying up late for us.
No, not so. Okay.